Okay, let's continue. So we find out that for reciprocal matrices, eigenvalue will be reciprocal to each other, but we haven't discussed what is physical interpretation. We said that the eigenvalue or the eigen value will be in the form of one will be exponential c and the one will be exponential minus c, but we haven't said discussed the what does the c mean. So the first case, if the c is pure imaginary, yeah, since the matrix element has a imaginary value, so it's definitely could be imaginary. So okay, so let's call if it is actually pure negative pure imaginary value, so it is actually, we can write it down as exponential I c and exponential minus I c. Okay, so in such case, the eigenvector after field propagation doesn't change its the absolute value. So let's consider if the grating has n period and the eigenvalue is pure exponential I could see, so it's only in the form of a phasor. It doesn't change its magnitude. So if we see that we do the e final or the eigenvector in the other side taking a square, it will be a exponential I m c and e plus or minus this eigenvector. So this is 1. So it actually has the same the same moduli of the input eigenvectors. So the input, yeah, no matter you see the left side as the input or right side of the input, you will see its strength is actually the same, but it's just turning its face the shift a little bit with the same phase delay after shifting and after passing through one period. So in that this kind of structure probably can manage its manage its phase, but you cannot make a very strong reflection of light from one side to the other side. But if the second case, if the c is purely real, so that means the power will exponentially decay or growth after passing the grating from one point to the other point. So for example, if we take the positive c, so it's strong, becomes strong a little bit, and becomes stronger and stronger and stronger. So that will end the eigenvector of one side has a much higher value of the eigenvector from the inside. However, since we let the dielectric has no optical gain, so how does the power leaving from the left side comes from? It cannot be due to the input from the left hand side. Yeah, it's not possible because the dielectric doesn't have providing any gain. So how does get a high output power leaving from the left side? It can be caused by the input power from the right side. Input power from the left side as well. So that means we have a strong input and a strong output from the same pole, and this is caused by a very strong reflectivity. All right. So if we do the if we can make the transmission many pairs, so and we will see the input or output out will go to 0 or vanish. So that means we are actually making the reflectivity goes to 1. All right. So how can we achieve a pure real eigenvector by the properly assigned layer thickness? The rule of thumb is that we can decide the thickness as lambda over 4n. Lambda b means is target reflector. Yeah, target reflecting wavelengths. For example, you can change your targeting wavelengths at 400 to 420 nanometer. Is in a violet region. It's a violet light. Okay, and we can have two alternating transparent dielectric. One choice is SiO2, and its refract index is usually around 1.5. Or you can choose another dielectric with a higher refract index. For example, a very common one, titanium oxide. Or you might also choose the NB205, which also has a pretty high refract index in the short wavelength region, which could be 2.3 even to 2.5. Okay, so the Bragg index, the Bragg condition of such wavelengths will be, and for SiO2, for example, will be 420 divided by 4 times 1.468. How many is that? So it's okay, the answer is here. It's around 7.15 nanometer. And for the TiO2, it is the Bragg's condition. It is 420 divided by 4 times 2.294, and it yields about 45.8 nanometer. All right, and the reflectivity between the SiO2 and the TiO2 interface has a true value. The reflectivity from SiO2 to TiO2 here, yeah, will according to the Fresnel equation, it will be here it's a around negative 0.22, and it is a negative value. But for the reflection from high index to low index, aka from the TiO2 to the SiO2, then we get a positive value of the positive value with the same magnitude. It will be 0.22 here, for example. All right, so now we can try to evaluate its discrete propagating constant by finding the trans matrix of one pair first. So what does one pair? One pair means the light underwent first one interface, one median, and then second interface, second median. Okay, then repeat itself. So two interface and two median forms a unit of a Bragg's reflector. Okay, so this is the interface 1. So let's use the right color. This is the interface 1, T1, and this is T1. And this is T2, so here it is T2. Then the second interface is T3, so this part is T3. And finally, the second median is T4, and this is the T4. Okay, so we said that the median has it has a eternal exponential j beta L, and now beta is let's assume there's no loss or gain for the material, so beta will be lambda over 2 pi n, and the L is intentionally designed to be lambda over 4n. So after canceling the common terms, it yields the phase difference will be half of pi for each layer. Alright, so the exponential I pi divided by 2, this is I, and okay, just use the same color, and this is I, and this is minus I, and the same, this is I, and this is minus I, and since the reflectivity here and here is different, it's in negative value, so we just write it down, the plus term as R and the minus term as a minus R. So the direct multiplication is simply done by here. So we have 2 T over 1, we can put it out first, and the I, it will be T square over I square, and times 1 R1 times, since we will already pull I out, so it will 1 0 0 minus 1, again 1 minus R 0, and 1 0 0 minus 1. Alright, so it becomes T square over minus, and I square is minus 1, and the first term become, the first two is 1 R minus R1. So this is the combination of these two. And the second combination is 1 minus R, and the 0 goes in, and so plus R, and plus, okay, here it is 1, sorry, plus R minus 1. Okay, so do it again, so it becomes T square minus 1 plus R square, and 2R, and 1 plus R square. Okay, so the transmission matrix of one pair dBr looks like this. So we can see that the T11 and the T22 is the same, and the T21 and the T12 is the same. And we can put it into the expression of its eigenvalues. And since T11 is equal to T22, so we just taking T11 as an example. And we have the final expression of your eigenvalue as T11 plus square root T11 square minus 1. Alright, so for simplicity, we assume a pretty common scenario is that the dielectric layer are lossless. Yeah, we just assume we deposit a pretty good film. It will further simplify its the expression. So for a lossless value, we already said that we have a relation here. So the T11 square minus 1 can be replaced as T11 minus the 1, it should be T21 square, and take a square root on both sides will be t to 1 plus or minus. Alright, so the exponential plus or minus c, yeah, with a different sign, will actually be equal to t11 plus or minus t12. Then we can further put in t11 and the t12 here. Yeah, then we get the reflectivity of one pair as the reflectivity of one interface. Yeah, a function interface. Yeah, this R is the reflectivity interface, and this is the the eigenvalue of the one pair dBr. Alright, then we can further expand the result here as described in previous page. We find that if we take the positive term, the exponential c is t11 plus t12. So it becomes t1 plus t12. So the AB, the ratio between the input and output power will be equal to 1. Similarly, if we take the minus term for here, and the final result will be the ratio between A minus and the B minus will be minus 1. Okay. So it turns out the eigenvector can be representative as 1, 1, and the other negative eigenvector can be written down as 1 and minus 1, since it's a ratio. The ratio here is 1, and the ratio here between input and the output is minus 1. Okay, so what's the reflectivity of the one pair mirror? So we can consider a scenario that the light is coming from here, and so we have some A1, but the other side don't have any power, no input. So the output vector will be A and B is 0. Alright. So let's consider the power from the coming from here, and this is the matrix with m times. Alright. So we can write it down the vector A0. The right side, that will be easier, then probably easier, more correct to say that. The A0 can be decomposed into its eigenvector as half of A0 with 1, 1 plus 1 minus 1. So since if we can decompose any vector with its eigenvectors, the transformation or the mathematics will be much easier. Alright, so let's see what happens if the right side is 1, 0 vector. That means the output power from the right side is 0, but no input here. Alright, so we write it down as 1, 0 as half of 1, 1 plus half of 1 minus 1. Alright, so just like this. Okay, so because for the plus eigenvector, we will get the exponential c, and for the negative eigenvector, you will get the exponential minus c. Alright, so now it becomes half of the exponential c plus half of exponential minus c and the exponential minus c. Okay, it becomes half of exponential c plus exponential minus c, half of exponential c minus exponential minus c. Okay, so it is deduced into cosine c and the sine c. Alright, so the A1, B1 here, the input is proportional to hypercosine c, and the output is proportional to the hypersine c. Since there is no input from the right hand side, so the ratio between B1 and the B2, it means its reflectivity. Yeah, because in the output of the left hand side, there will be no composition from the right side, so the power is totally from the input of the left hand side as well. Alright, so it is due to the overall reflection, yeah, from the input. So the reflectivity of one pair dBr can be written as sine c divided by cosine c, hypersine c divided by hypercosine c, and it becomes the hypertangent c. Okay, so this is a case of one pair. Alright, so we can expand such formalism with arbitrarily many pairs. So let's consider n pair of dBr. So the overall transmatrix will be the matrix of one pair times m times. So probably should be more precisely the m pair. The transmission matrix of the n pair dBr will be the transmission matrix of one pair dBr times m times. Okay, and we also put the input power as 1, 0, since it has only one output, no input. And with a similar procedure, we will find that the input, the left side has the input of cosine m c and sine n c, because the eigenvalue for one pair is exponential c, and it times m times 1 times 2 times it times m times, so it becomes exponential m c, similar for here. Okay, so with n pair dBr, the overall reflectivity will be written down by hypersine m c divided by hypercosine m c. It will be hypertangent m c. And recall we have the exponential plus minus relation here, and we further deduce that for the plus term, it will be actually be r plus 1 divided by r minus 1. For the minus term, it will be r minus 1 divided by r plus 1. And we have the r is equal to n2 plus n1 divided by n2 minus n1. And put it in and do some rearrangement. So the exponential c can be written as minus n2 divided by n1, and vice versa. Now the reciprocal one will be minus times n1 divided by n2. Okay, then we have the hypertangent c. It is exponential and c for m times minus exponential c for m times as well, and exponential c for m times plus exponential minus c for m times, and plug it in. Finally, it becomes the equation here: n to 2n power 2n plus n1 power 2n divide n to 2 power 2n minus n1 power 2n. Okay, so we plot the reflectivity with number of pair, that the number n, with assuming the same common n1, the low index one with 1.5, and the high index one we try the free value, one is from low to high to be 1.6, 1.8, and 2.2. And you will see if the reflect index difference delta n is n2 minus n1 is large, you will get a high reflectivity for any pair. Yeah, higher and higher delta n. Okay, so if we have a more strong reflectivity difference, and we will get a high reflectivity very efficiently. For example, if you want to get a 0.9 R is equal to larger than 0.9, you will see if you have a delta n as high as 0.7, you only need 4 pair. But for the n is equal to 1.8, probably you need it to be 9 pair. For n it is 1.6. Yeah, delta n, in this case, delta n is only 0.1. Yeah, probably 20 pair doesn't have a make it. You need to try to find it out. Probably will be 22 pair or something like this. Okay, so how do we explain the DBR works? So that's besides do a direct mathematical the metric multiplication, we can consider as this. Okay, so that would So let's consider the light is coming. You actually have a laser. You have your laser light. Okay, coming from here, and since n1 is let's consider n1 is lower than n2, so part of ray will be reflected at this interface with minus r. So when it times minus r, it's actually it gives a plus pi phase shift. Yeah. Okay. So let's console. So the reflected ray has a pi a phase shift of a pi after the reflection, but part of them will passing through the interface, and the passing through the interface doesn't cause any phase delay, and the thickness is lambda over 4n, which gives us a pi L to be half of pi. Okay, so half of pi here. So it will give a half of pi delay passing, propagating to the right direction. And in the second reflection, since it's from the high index to the low index, so the R is positive. So the reflection basically doesn't add any phase change with that. Okay, so the inverse propagation add another 2 pi. So the optical feedback after the round trip in the second layer gives a total pi here and back to here. So the phase difference between the first reflected ray and the second reflected ray has no phase difference. Is delta phi is 0. So it is in the two reflected way is in constructive interference. Okay, let's clean and do another scenario. Okay, so and we can similarly we have no for the N2 N1 interface, the reflection here doesn't cause any pi shift, but in the second layer you have a half of pi propagating and to the right, toward the right, and have a half and the pi phase delay due to the second due to the second reflection and another half of pi. So the round trip in the second layer gives a 2 pi after such a trip, and compared to the reflective wave, in such case, the phase difference will be 2 pi. Yes, it's actually the same scenario of the 5 to 0 as well. So it's still also perfect constructive interference. So the only change is that if the reflectivity for one pair and is high, the accumulation of the total power will be more efficient, so you can obtain a higher overall reflectivity with less pair. So this is only a reflectivity. So if we are talking about energy and the power, reflectivity is for electric field. Yeah, but we are talking the energy of power. You need to do the reflectance, and the reflectance will be square of the reflectivity. So G means grating. It is the reflectivity calculated by the equations above. And sometimes if the Rg is not pure real, you need to remember you need to do the Rg squared to be Rg conjugate times is Rg if it is a complex value.